Hey everybody. I'm actually going to force you to sit through my intro as well, so sorry. I'm going to be very well introduced. But yes, my name is Dave Josephsen. I am currently the developer evangelist at Librato. I wanted to be real clear that this isn't, in fact, Dr. Neil Gunther's talk, which is actually one room that way. So if you're looking, cool, I got the arrow right. So if you're looking for Dr. Neil, right next door, which you should be, honestly. But for those of you who are staying with us, I'll give you some background on me. I have been an attendee very long time now, or at least it feels that way. I've been attending since about 2002. I did win Best Paper in 2004 for spam. Remember we used to talk about spam, and that used to be a problem? Awesome. Today I write the monitoring column in Login Magazine. I've also co-authored or authored a few books, all of which have squiggly things on the cover. So I tell people, which I tell people because it's true, that I am the world's foremost authority on writing nonfiction technical books with squiggly things on the cover. So if you are in the market for a consultant who's very good at writing technical books with squiggly things on the cover, I'm available. You'll find my contact info just there in the center of your screen. So today, anyway, I want to talk to you about how we data storage at Librato, which is actually a very deep subject that I'm really only going to be able to scratch at today. But I'm going to talk about our data design and sort of how we arrived at the data design that we use, which is sort of a non-standard one for time series databases. And then I'm going to talk about our persistence layer itself, which is Cassandra. So super short background on Librato so that you understand what we're trying to achieve here, and not because I'm trying to sell Librato. We are a monitoring software as a service. We're basically implemented as a REST API. So the model is that people configure their monitoring tools to emit metrics to us. We catch the metrics, we persist them, and then we provide the suite of tools to like visualize and correlate and alert on stuff. So we get a lot of these singular data points from a single thing that someone out there is trying to measure. And sort of historically, the systems designed to store these things have regarded them as a named sort of date value tuple, which is a very simple way to think about it. But it turns out that this is actually kind of untenable in the context of a multi-tenant time series database. And there's sort of an interesting story behind why and how we eventually arrived at not using these anymore. And that's what I'm here to tell you today. So if we consider that this thing is a float, and we measure one of them per second, and we persist all of those for a year, we wind up with about 250 megs in our persistence layer. If we measure 100 of them, our storage requirement jumps to 25 gigs. And if we measure 100 things on 100 servers every second for a year, we wind up with about 2.5 terabytes of data in our persistence layer. And this isn't the end of the world. Like, you and I could go out somewhere, probably on the street today, and buy a 3 terabyte hard drive to store all of this. But when you consider what you actually have to do to draw a graph when you hit a data volume of this size, drawing the graph becomes sort of a non-trivial exercise. You actually have to take a user-specified time range. You have to seek and extract the block of data that you need out of your data store. And then you have to package it up and export it to a UI that's capable of graphing it. And for the user experience to not suck, you basically have to do this on the order of 100 milliseconds full stack from UI to persistence layer back into the JavaScript library running in the browser. So seeking across terabytes of data on the order of milliseconds and doing something useful for it like this is kind of approaching a Google scale problem. And at shops like Amazon and Google, where they have these huge, crazy amounts of data to process in under millisecond times, they use, or under second times I should say, they use sort of these large-scale parallel processing techniques to break up the workload. But time series databases don't do this. In fact, just about every database that has ever been conceived that was designed to store time series data uses something called a consolidation function, which I'm sure you're familiar with, to avoid making this a big data problem. So let's say, these measurements were taken about 10 seconds apart. There are 12 of them, which leaves this time series at about 120 seconds, or 2 minutes in total length. Consolidation functions basically work by computing a new data point that summarizes the data at a decreased resolution, right? So the choice of how this is done is up to you, but almost all of us always choose average, and that's on us, but whatever, we'll take that hit. So in this case, we might average each of these sort of 1-minute intervals into a single data point, one each to summarize the minute. And what's happened there is all of those sort of data points on the bottom have been averaged into a single data point, right? We do this over and over and over and over and over and over and over again, usually in a ring buffer data store, just taking a whole bunch of data points and re-averaging them down into fewer data points. So this solves our big data problem. It solves our storage problem, and it solves the problem of how we're going to churn on all of this data. And it costs us basically some resolution loss. But it turns out there are problems with this in multi-tenancy, the first one of which is you can't make that decision for the people who are sending you the data before they send you the data. And you aren't going to get a lot of signups if you're sort of waiting there for them to decide something like an RRA before they emit a data point to you. And you don't want to take the graphite model of kind of assuming that what they want is an average, because averaging data is actually a very sort of non-trivial data loss. Averages have a way of deceiving us with the truth, right? And using the arithmetic mean in this context is very damaging to data in general, because averages smooth our data, which is especially harmful in the context of monitoring computery things. Those of us who want to draw these graphs also want to see these peaks and valleys. The peaks and valleys are actually kind of the interesting stuff. The average of the peaks and valleys is far less interesting. The second problem is that averages are not necessarily distributive, by which I mean that the average of the average is not the average. This is a subset of the Simpsons paradox problem. So if we take the average, or if we ever in our data store take the average of already averaged data, which turns out to be surprisingly easy to do in systems like Graphite, we actually run the risk of returning a mathematically incorrect answer. And it'll be incorrect in the context that the answer we get back will be usually even smoother than the average, right? So what other options do we have? We basically have a handful of options available to us, just if we're not getting into, really crazy math. Assuming that these 5 values here were taken about 12 seconds apart, what computation can we perform on these to sort of summarize this minute's worth of data in the most sort of statistically significant way? And the answer kind of depends on what we're measuring. Sometimes it makes sense to throw out all but the smallest or largest argument. Weird. So right now the 3 and the 6 should be yellow and everything else should be grayed out. So keynote bug, sorry about that. Sometimes it makes sense to throw out all but the smallest or largest measurements. We might keep the largest when we care about things that might get too big and we want to prevent that from happening. So imagine for a moment that this is a graph of CPU load over the last couple days. So the top line, which displays the maximum measurement in each interval for each minute, is basically way more of an accurate depiction of the thing that we care about, right? We want to know basically the maximum for CPU. Or if we kept the minimum value, we would want to do that in the case that we want to make sure the thing that we're measuring doesn't go below a value. So now reimagine that this is a graph of the available worker thread counts, right? And basically the bottom line shows us the fewest available workers for each interval in our data set. And that's a way more sort of statistically significant value for us than either the average or the max lines, obviously. So we have other couple of options. We could keep either the sum or the total count of measurements in this series, the cardinality of the series, basically, preserve the cardinality. And these are actually more interesting than they sound at first because, for example, if I have this user and this user is making a request to this website, and every time he does this, I just count these requests as they happen. The cardinality of those connections tells me a few things. It tells me the total number of requests that I've gotten, and therefore it also tells me the rate of requests per interval. So if I'm already measuring something like the latency or load time here, preserving the cardinality of the set gets me 3 metrics for the price of 2. We get latency, we get number of requests, and we get rate, right? If we also keep a running sum as well as the cardinality, we can compute the averages using, well, the cardinality divided by the sum divided by the cardinality. And that solves our distributive problem, right? This is a way to actually preserve a rolling average in a way that will never be incorrectly computed later, right? Every time we need the average, these two numbers give it to us, and we can compute it at display time. So cardinality and sum kind of pay for themselves. If we keep them, we get distributed averages, and we get rates for free. So here's another interesting idea. If we can compute the mean using the sum and the count, maybe we could add some context to the mean in a running way by keeping a running tally of the standard deviation from the mean for this set, right? So imagine I have this crazy amount of data, and so much that it's like hard to even see patterns in it anymore. And the problem basically is for any size of data set, a really huge one like this or a single data point all the way up to a zillion data points, we basically want to have a handful of numbers that describe the data set, summarize it in a way that's statistically significant for us. And by that I mean we literally have 77,431 data points right now in this graph. Those are 77,000 measurements, and basically our goal is to condense 77,000 into basically a handful of numbers that give us the truth of this set without deceiving us, right? So there are a lot of individual values here, but they're all between 0 and 35. So we could draw a histogram of this, and we can see how the data is distributed. It looks like about 40% of the values in my graph are between 0 and 1, for example. The green dotted line, or the green dashed line, gives me my mean, which in this case is 4.75. But we can see that a lot of our data, just by looking at the histogram, isn't clustered around this mean. So it turns out, when we compute standard deviation on this, it turns out to be 5.15, which is enormous. So these two numbers together, right, the mean and the standard deviation, or sigma, give us a good idea of how volatile the set is, right? So, okay, clear your minds, forget everything that I just said. And we'll rework this by the numbers. Imagine I walked up to you and said, hey, I have some data points. The mean's about 475. And you're like, okay, yeah, your thing is about 5, basically, right? But then I tell you, hey, the sigma for that is like above 5. And you're like, oh, well, yeah, I don't know anything about your data anymore. It's completely, that's meaningless to me, right? Like, you haven't said anything about your data. But then I tell you the sum, and the average kind of becomes meaningful again. If I have a mean of 5 and a sum in the hundreds of thousands, you can at least kind of think about the magnitude of my data. You can think about how much of it there is, right? When I give you the count, you don't need the mean anymore because now you can compute it for yourself. And if you have the min and max, well, now you have a pretty good description of this set. We have 77,000 data points ranging between 0 and 35. I have the deviation. I can compute the mean. So what if instead of just keeping the value and date for this bunch of data points when we roll them up, what if we actually keep this whole blob of spread data per data point, right? It increases our storage value by about a factor of 5, but it's probably worth it for what it tells us about any size of data set, right? So one really interesting property about these, I'm going to call them fat data points, is that they self-summarize, by which I mean as a software architect, every time I need to combine any number of these data points together, I computationally do the same thing, right? I add up the counts and sums, I keep the min of the min and the max of the maxes, and then I'm done, pretty much. So it actually doesn't matter if there's 77,000 data points behind these or if there's 5. I'm computationally doing the same thing every time, and what I get back is actually this sort of meaningful chunk of data, right? I can't actually keep a running standard deviation, but I can compute standard deviation. because that is equal to the sum of squares divided by the cardinality, right? So basically, here is a self-summarizing data structure that consolidates in a way that will continue to give me a solid understanding of the set it represents, even when the set ranges into the zillions of data points. If I wrap that in some JSON, give it a name, a date stamp, here's our data structure, right? Oh, sorry, go ahead. I'm sorry, I had a long time ago. So yeah, I mean, it is what it sounds like. It's basically a sum of the squares of, yeah, of the values of the data points, yeah. So if I took all my data points and squared them and then added the, yes, that, yes. Sorry. So here's what we want to store. And I should mention, I'll back up for a second. So that's cool, it's mathy, awesome, we like math. But there are reasons beyond just wanting to avoid averages to choose this data structure, one of them being user experience. Because if you take the traditional approach, right, if you say that we're going to store this metric, and this metric is basically a date and a value, which is what we're doing today with RD tool and Graphite and all of these other tools. The implicit contract is that, well, you're going to give us some data, and you're going to slowly, and we're going to slowly destroy it for you, right? Like over time, like, and yeah, and by the way, we're going to need you to make that decision up front. Like before you ever get to see what your data is going to look like after we destroy it, we're going to need you to choose, right, the form of the destructor. We're going to need you to choose the mathematical technique that we're going to use to kill the thing that you love. And having decided it, there's no going back. Like you can't change the summarization function without manually rewriting the data, most of which has already been destroyed, right, into a new data store. But if you keep spread data, if you keep these fat data points, you can postpone the decision of summarization function until display time, right? I actually give my users the opportunity to craft a single graph like this one that is showing the same metric 4 different ways. It shows the min, the max, the average, and et cetera. Anything that I have in that data store, I can display basically at display time, obviously, right? I can even present a menu that sort of just allows my end users to change their choice of summarization function at graph time, at the cost of a marginally larger back-end storage persistence layer, right? I'll pause. Yesterday I had like 98 slides in my presentation, and I finished 10 minutes early. Which is like, you're talking too fast, dude. You know metrics. Sorry. Okay. So now we have a pretty good idea of what this thing is that we want to store, right? We know what's inside it. It's basically going to be a JSON blob of spread data. The question becomes, how are we going to store these? We're going to be getting lots of them per second. And we basically need a data store that's not going to fall over because we're, again, making a multi-tenancy sort of time series database here. So we have some intense requirements for this persistence layer. It has to be resilient to hardware failure. It has to be capable of like linearly scaling, which means it has to get faster when I throw new hardware at it. It has to be able to scale past trillions of writes per second. It generally has to return from any reasonable read or write operation on the order of about 50 milliseconds. Ideally, that would be awesome, right? It probably needs to be a general purpose database. It can't be special purpose because it has to satisfy some multi-tenancy needs. We need to be able to, for example, implement application layer permissions on it to keep one user from seeing another user's data, and et cetera. So there's no ACID system in the world that's going to be able to satisfy our scalability requirements. And all of the sort of special purpose databases are kind of out because they don't satisfy our multi-tenancy stuff, which is a bummer. But thankfully, we can make a few trade-offs. We're writing time series data here, so our write model is generally going to be append only, right? And therefore, we can sacrifice mutability in the data store. And I should note that what we're really giving up here amounts to a convenience operation, right? Because our data points are already sort of designed to really be easily really be easily combined together. So if we need to backfill some data, if I have a data point that gets here 20 minutes late, I can go ahead and grab the data out of the persistence layer from 20 minutes ago, create a new data point by rolling together those data points by adding up the sums, keeping the mins of the mins and the maxes of the maxes, like I said, and just sort of slapping a new date stamp on it, and then just appending it to the database and tombstoning the old data. We can also sacrifice some consistency. We don't literally need every single measurement to exist everywhere in the persistence layer immediately before we can draw useful graphs, right? We can more or less draw what's in the data persistence layer now, and it'll reflect reality plus or minus a few seconds, which is fine for most use cases, right? So given these trade-offs, Cassandra is basically custom tailor-made for our purposes. It was dropped from Erebus on a golden whatever. If you aren't familiar, Cassandra implements this ring architecture. It's made up of hosts, each of which basically has a copy of some subset of the database. You can write to or read directly from any single one of these nodes in the ring. And when you write to something, the node that receives it uses a partition key to split that data off and send it to the hosts where it belongs. If I lose a node in a Cassandra ring or a combination of nodes in a Cassandra ring, every node knows the location of an alternate copy, so reads and writes both sort of continue as they normally would. And then when the host or combination of hosts comes back up online, Cassandra basically just brings them back up to date before marking them available to be put back into the general population. Right? It's hard for me to articulate how wonderful this data store is. It's very, very, very nice. That was 3 adverbs, nice. It's very scalable, very stable. It is eventually consistent, so if you read from 2 nodes, you may not get the same answer, but that's fine with us. Apple and Netflix both have a huge infrastructure investment in Cassandra. A few weeks ago, Amazon did their huge Zen vulnerability reboot thing. Maybe it was a couple months ago now. And when they did this, Netflix, I don't know if you read the article, lost 218 Cassandra nodes, 218 systems in their data persistence layer, right? The database that houses their online video streaming product just switched off at Amazon's discretion, and the Netflix service didn't even blip. At Librato, we've survived both RebootGate and the recent sort of Zen. Wait, that is RebootGate. What was the one a couple years ago? Cloudpocalypse. We also lived through Cloudpocalypse, and we are in US East, so Cassandra is kind of amazing. At Librato, we run 2 Cassandra Rings. They are composed of 33 instances. These are I2 extra larges or thereabouts. Inbound metrics are initially written to our raw ring, so there's a fast write path directly to the raw ring, and then a back-end process basically reads the aging metrics out of raw, consolidates them together, and writes them to the roll-up ring. So you have raw data available for the first however many moments, and then you have sort of consolidated data after that. Our stream processing tier handles about 12 billion inbound metrics per day, which is, I think, on the order of 140,000 a second with 60 millisecond mean latency. We sustain around 600,000 writes per second and burst into the 800s. Our bursts usually last around 20 minutes to an hour. Our write latency is about 25 milliseconds, mean. I think that you can read it, the P95, I think, is up around 75. We do 3,000 full stack writes from the front of our API all the way into our persistence layer per second with an 80 millisecond mean latency. Those are reads sort of generated by users looking at graphs. Specific to Cassandra, we do about 15,000 reads per second with a 10 millisecond mean latency, and that'll be one ring reading from the other ring to do long-term storage rollups. However, like most of the awesome tools that we all know and love, Cassandra is not without its quirks. I'll show you really quickly sort of how we're internally architected. We're basically a big signal processing system for metrics data. So metrics kind of come in on the left, and get persisted on the right. All of the colored boxes that you see between those 2 points are microservices implemented in various languages that process metric data in one way or another. Looking at the persistence layer specifically over on the right, you'll notice that all of the read and write paths for all of these services terminate in a single service called Boatman. And Boatman is a Java service that we wrote that arbitrates access to our Cassandra rings. So none of our services are allowed to write directly to Cassandra. All of our services use a service that writes to Cassandra. And we do this for a couple reasons. The first is that Cassandra clients are not necessarily created equal. We've had some pretty large problems actually in the client layer with Cassandra clients not noticing that nodes are up or down and just being generally wonky in various failure scenarios. So Boatman standardizes us on the best possible Cassandra client available. I think right now we are still on the AskNax client, and we are, if you're Cassandra adept, we're playing with CQL, and we'll probably move Boatman to CQL. Second, we've found that very long rows, which if you read the Cassandra documentation is sort of a beloved feature of Cassandra, slow down reads immensely. So the longer these rows get, the more data we allow to go into a long row in Cassandra, the more SS tables Cassandra writes on disk. And so what will wind up happening is we'll end up getting these read blocks where a customer says, give me the last 2 weeks of data. And Cassandra actually has to go random seeking across the file system to find all of the SS tables that contain the data they need. And that makes for very slow reads. So we've solved this by using a rotating prefix, basically. Inside of Boatman, as a service, I write my thing to Boatman. Boatman actually renames it with a prefix that rotates every 6 hours. And then Boatman knows how to find it later when I ask for it, right? So Boatman sort of enforces row length. We have a predictable row length size inside our persistence layer because Boatman is sort of arbitrating that access for us. We've also done some tuning to make Cassandra's internal compactions more efficient. We TTL a lot of data, something like 800,000 metrics on the minute, somewhere in there. I haven't actually looked lately. But when Cassandra TTLs out a data point, it doesn't delete it. It tombstones it, which is a problem, because then you're left with all of these SS tables that literally contain nothing but tombstone records. And then compaction comes along and line by line, row by row, actually tries to expunge all those tombstoned, all of those tombstoned records out, which is a huge problem. It directly correlates with read and write latency. So we basically have some hacks into data core that compare for each SS table on our system the SS table's C time to our TTL. And if the C time is older than our TTL, we just delete the entire file, which is a nefarious hack, but it works. And then finally, synchronization has probably been enemy number one for us running a Cassandra system. I'm really not sure. If you're like from Apple and you know about their Cassandra tier, I would love to know how other people are managing this. But basically what happens is these quasi-related processes that aren't in Cassandra at all, like JVM garbage collection or an FS trim cron job, will come along and happen on like 3 nodes, and those nodes will all have the same data on them. And if it's FS trim, we're literally blocked, waiting on CPU. So we can't make any writes, right? So we have to make sure that processes like these don't synchronize. I've graphed it here for you. The blue-green section here is actually Java garbage collection activity. And I've overlaid read latency here in orange and purple, so you can see for each of our Cassandra rings how read latency correlates to just JVM garbage collection on the back end. So we have to be very careful when we have an update or a fix or something that causes us to restart Cassandra or the instances that Cassandra is running on to not do them all at the same time. We have to sort of stagger those maintenance jobs so that these things don't synchronize. So that's all about I probably have time for today. But I'd love to talk more about Cassandra and or data storage in general. I didn't get into any of the dimensionality stuff that we do, which I think is super cool also. So I hope you have enjoyed our time together. I know I wasn't as funny as yesterday, but yeah.
To what extent could you extract these tools and apply them at another site that wasn't yours? Is that, I mean, aside from like writing it all yourself from scratch somewhere else, is this, you know what I'm saying?
Yeah, it's tough that so much of this we can't give back. So the big reason that I harp so much on fat data points right now is that I would really like to see like implementations of the spread data, structure in databases like Graphite and RRD tool. And honestly, having had those conversations with the guys who could do that, we're actually, as users of these tools, capable of making these decisions for ourselves. Like I can create RRAs or the equivalent in Graphite to store, min, max. I can store the whole litany of RRAs separately, but I kind of have to know that I want it up front. So that whole section is kind of halfway me like, hey, look how cool these are. Hey, can we get native support for these? And also, hey, you guys could be using them too. You just kind of have to know what you're doing with RRD tool and Graphite to use them. The rest of it, yeah, the rest of it is all very snowflake. Yeah, it sounded like, so now I have it all stored, how do I graph it?
No, the question is, if the standard tooling is already averaging it for you, how do you, Librato, get the right data?
Oh, we replaced the standard tooling. So the question is, thanks for that one, by the way, no. So the question is, like, yeah, if the standard tooling isn't doing this, how do we accomplish it? And yeah, we're basically a Graphite replacement. I mean, you can think of us that way. There's more to us than that, but yeah. So we would work with collectd, statsd, whatever instrumentation libraries you're using, and we get raw data. So yeah.
So I've got a little familiarity with a database called PyHistorian. It's a proprietary product, so they don't talk quite as much about what they do, but could you compare your compression to that if you know?
What's the name of it?
PyHistorian.
PyHistoria.
Yeah, it's also a time series database. But if you haven't heard of it, then
I'm completely ignorant of it.
Okay,
so
well maybe we can chat later about it.
Judge me.
Yeah.
I'll definitely Google it after this.
No, it's fine. It's used in the energy industry a bunch.
Oh, okay.
Yeah.
Nice.
So you said you're using SSDs. Do you think it would be possible to get the performance that you need off of spinny disk, or would SSDs be a strict requirement to handle it?
It sort of depends on the use case, right? So we actually have for a while run traditional disk nodes in our roll-up ring, because that's not necessarily like a time-sensitive use. We've been SSDs as quickly as we could be SSDs, and are looking at in-memory data stores for for the raw ring, because yeah, that we definitely need that fast write path in, so we don't drop stuff on the floor. But yeah, I would say it depends on your use case. I have pretty good numbers on what the difference is, by the way, which I could probably share with you, or at least let you glance at. Yeah. Cool. Thanks, guys. Oh, hey. I probably should mention I have the office hours thing tomorrow, well, tonight at 4, and then tomorrow again at 10:30. So if you guys want to talk about monitoring stuff, be thrilled.